In section 10.2a, we're going to be doing hypothesis tests for a population proportion using a method that's called simulation. And then in the following section, 10.2b, we will look at hypothesis tests for a population proportion using a model, the normal model. The expectation is that by going through the method of simulation, we'll have a better understanding of what the normal model is doing for us, which is the more traditional approach using the normal model. This method of using simulation is relatively new. We are able to use this method to discuss hypothesis testing because of the fact that we have such powerful desktop, laptop computing tools available to us.
Right.
This method is, the expectation is that it has intuitive appeal and therefore helps us to better understand what the normal model is doing for us. So in section 10.1, we introduced you to the language of hypothesis testing. Our goal now is to discuss a method for testing hypotheses about a population proportion. And so in these tests, the null hypothesis is always a statement of equality. So the null hypothesis is going to be that P equals some value. The proportion equals some value. Generically, I'm just going to call that P sub 0. And then the alternative hypothesis is going to be structured one of three ways depending on what your research goal is. You could have a two-tailed test, which is the proportion is different from P naught in your null. You could have a left-tailed test, in which case the proportion is less than P naught in your null. Or you could have a right-tailed test, in which case the proportion is larger than P naught. And again, this P naught that I'm saying here is simply a proportion between 0 and 1, and it's referred to as the status quo or no change, no effect value of the population proportion. Whenever we do any kind of hypothesis testing, it's super important that you understand that the statement in the null hypothesis is always assumed to be true, and we're looking for evidence in support of the statement in the alternative hypothesis. So this again falls back on that analogy of the court system. The null hypothesis is innocence and the alternative hypothesis is guilt. We always assume in a trial that the null hypothesis of innocence is true, and we're looking for evidence in support of guilt, and that's what the jury makes a decision on based on the sample evidence, which is the evidence presented by usually a district attorney. So let me go through the logic of this simulation method with a scenario. At Joliet Junior College, the proportion of students who pass intermediate algebra is about 0.5. In an effort to increase the pass rate, Professor Grant Alexander decided to start flipping his class. Flipping refers to the idea that lectures are recorded on video and watched at home by the student so that class time is utilized for homework, group learning activities, and explorations. So in Professor Alexander's intermediate algebra course where he flipped, 29 of the 50 students passed the course. And so the question that we have is, do the results suggest that pass rates in Alexander's intermediate algebra course have increased? That's what we want to know. Does that sample evidence suggest that the pass rates have increased? And so let's form our null and alternative hypothesis for the study. Remember, the null hypothesis is always a statement of no change, no effect, no difference. That would mean that the results in the flipped classroom are the same as the results of intermediate algebra in general, namely that the proportion who pass is still 0.5. And then the alternative hypothesis is what we're trying to gather evidence to show, namely that the pass rates in the flipped model have increased. this would suggest that the proportion of students who pass is actually bigger than 0.5. And so now let's look at our evidence. The sample proportion of students who have passed, p hat, is the number who passed, which is 29, out of the number in my sample, which is 50. So 29 divided by 50 is 0.58. So on the face of it, at least based on the sample evidence, the sample proportion of students who passed is certainly bigger than 0.5. But the question is whether or not this pass rate of 0.58 is statistically significant. In other words, are you convinced, based on just these 50 students, that flipping the classroom really has increased the pass rate beyond 0.5? And maybe Alexander should recommend that all instructors start flipping the classroom. Or the other possibility is, yeah, we got this sample proportion of 0.58, but the population proportion is still 0.5, and we just happen to get this result, or it's really not statistically different from 0.5. You could just get the 0.58 by sampling error or just by random chance.
Real quick, sample
Yes.
proportion is p hat x over n, right?
Yes.
Okay.
X is the number of, in this case, X is the number of students that have the characteristic passing, and N is the number in my sample size. And so this letter D is really a rhetorical question for you. We don't know whether or not 0.58 is statistically significant or not. What we're going to do is explore to see whether or not it's statistically significant. When observed results are unlikely, under the assumption the null hypothesis is true, we say the result is statistically significant, and then reject the statement in the null hypothesis. So to determine if these particular results are statistically significant, what we're going to do is build a model that generates data randomly under the assumption the statement in the null hypothesis is true. In this case, the proportion of students who pass is 0.5. That model is referred to as the null model because it, again, assumes the statement in the null hypothesis is true. We then compare these results of the randomly generated data in the null model to those we actually observed to judge whether or not the actual results are, in fact, unusual. And of course, this begs the question, how do we actually generate this random data? And we're going to learn actually two methods for doing so, but this particular problem lends itself nicely to using a coin flipping applet, or literally a coin if we wanted to. You see, we're assuming 50% of the students are going to pass the course. So a coin, we could say, all right, if I flip a coin and I get a head, that would mean the student passes. And if I get a tail, that would mean the student does not pass. And that's the randomness of it. The student has a 50-50 chance of passing. And so we're going to go through that logic in this activity. Okay.
Mm-hmm.
So if I had you live, what I might do is give each of you 50 coins and literally have each of you flip those 50 coins. Well, really what I'd do is give you one coin and have you flip it 50 times. And you would record how many heads you get out of those 50 flips. And we would compare that, and then I'd collect it from all of you, and we'd be able to start building out this null model. So I want you to have that vision in your head as we do this virtually using this coin flipping applet. And feel free to do this with me if you want. I'm just going to lay out for you how to build the applet now. So I'm going to go into StatCrunch, and I'm going to go under Applets, Simulation, Coin Flipping. The probability of getting ahead is 0.5, and I'm going to be flipping 50 coins. It's important for you to understand each of those 50 coins represents a student. So I have 50 students. And I want to know how often I'm going to observe 29 or more heads. The 29 comes from the fact that I actually observed 29 students passing the course. And I'll call this my intermediate algebra course. So here's what I'm going to do. I'm going to click one run and then explain what happens. So there's one run, and you'll notice that I observed, what I basically did there is flipped 50 coins. I observed 28 heads and 22 tails. The 28 heads that I observed means that I taught the class. Coming into the class, the student had a 50% chance of passing. Out of the 50 students that I taught, 28 passed this go around. Let's do this one more time. Now I'm going to hit one run again. This time, once again, the students have a 50% chance of passing because there's a 50% chance of flipping a coin and getting a head, a 50% chance of flipping a coin and getting a tail. I taught the class. Out of the 50 students that I taught, this time 22 passed. Now, ultimately, what I want to do is judge under this type of a situation where you have a 50-50 chance of passing, how many times do I observe 29 or more students passing the class? Okay.
So far, none.
So far, none. But I'm going to do this lots and lots of times. So I'm going to click 1,000 runs. When I click 1,000 runs, here's what's going to happen. We're going to pretend that I'm teaching the class 1,000 times. Each time I have 50 students, and the student has a 50-50 chance of passing. There we go. I'm going to do it another 1,000 times, and another 1,000, and another 1,000, and another 1,000. And so up here at the top, you'll notice that I had 5,002 different times I taught a class of 50 students. Out of those 5,002 times, 833 times I observed 29 or more passing. The likelihood of observing 29 or more out of 50 passing when the student has a 50-50 chance of passing is 0.1665. Here's what I want to make sure you understand is how to interpret that result. If the proportion of students who pass is 0.5, in other words, if the statement in the null hypothesis is true, we would expect to observe 29 or more students out of 50 passing in about 17 of every 100 classes. In other words, times we completed this experiment. Does this suggest to you that the class was effective? Because that was our ultimate goal here, is was this class effective? Put another way, would you be surprised to see 29 or more passing out of 50 if the real pass rate was 0.5?
I'd say no.
No, you're not, right? This result is not unusual. Therefore, we are not convinced flipping increases pass rates. What I want you to notice is one thing right out of the gate. What do you notice about the shape of the distribution of potential outcomes?
It's pretty bell-shaped.
Pretty bell-shaped. which suggests perhaps there are circumstances under which we could use a normal model to describe these outcomes. That's just a little foreshadowing for you. In this, the event was 29 passing, right? So that's technically what we call our test statistic, is the 29 or more passing. What I'm going to do now is go to Options, Edit, and I'm going to change from the number passing to a proportion, right? The proportion is 0.58, 29 out of 50. That was our sample proportion. Okay. And so now, when I click one run, it still does heads and tails, but instead of recording the number of heads down here, it's recording the proportion of heads. That's the only difference. So I'm going to do this another 5,000 times. And what I'm going to do is click Analyze. When I click Analyze, what the applet does for me back here in StatCrunch is it posts all the different sample proportion it obtained from each of the times that I did this simulation. And so you can see there's 5,001 sample proportions in there. If I drew a histogram of those proportions, that's the histogram that you saw in the applet. So these two histograms are supposed to look the same. They don't, primarily because of the fact that I'm using different class widths in each of them, but they are the same.
Okay.
But the bigger thing that I want to get out of this is I want the mean and the standard deviation of all these sample proportions. So if I go Stat, Summary Stats, Columns of proportion of heads, all I want is the mean and the standard deviation. So notice the mean of all those sample proportions is 0.4998, which is essentially 0.5. And remember, that was the proportion stated in the null hypothesis. That should not be surprising to you because we know the mean of p hat is going to equal the population proportion p, which is 0.5. And that's what we're getting here from the mean of all those 5,001 sample proportions. We know the standard deviation of p hat is the square root of p times 1 minus p over n. Well, we know p is 0.5, and we know our sample size is 50. If I compute that value, guess what it's going to be close to?
0.07.
0.07. Let's see. And lo and behold, this is approximately 0.071, which is what we're seeing there as well. In fact, it's 0.0707, which is exactly what we're seeing there. So think about this. The shape of the distribution was bell-shaped, which suggests we might be able to use the normal curve to model this simulation. The mean of the sample proportions equals the population proportion, and the standard error is close to the standard deviation of the p hats. So the description of the distribution of p hat is approximately normal, where the mean is p and the standard deviation is the square root of p times 1 minus p over n. All of this suggests that ultimately we can use the normal model to mimic what these simulation results are telling you.
Okay.
The bottom line is, right here, we learned that the likelihood of getting a sample proportion of 0.58 or higher from a population whose proportion is 0.5 is about 0.17. In other words, not at all unusual. This number right here, the 0.17 or 0.1665, is called a p-value. A p-value. Here's the definition of a p-value. It's the probability of observing a sample statistic as extreme or more extreme than the one observed under the assumption that the statement in the null hypothesis is true. Put another way, the p-value is the likelihood or probability that a sample will result in a statistic such as the one obtained if the null hypothesis is true. So for our coin flipping situation, our p-value was approximately 0.17. So that suggests that the likelihood of getting a sample proportion of 0.58 or higher from a population whose proportion is 0.5 is 0.17. You'd observe those results about 17 times out of 100, which is not unusual, and therefore we would not reject the statement in the null. We would not reject the statement in the null, and we would basically say there is not sufficient evidence to suggest flipping intermediate algebra increases pass rates.